Hello everyone, and welcome to our third Express webinar on Phoenix Win on Lin. Today we are continuing with our toxicokinetics example. As some of you may remember, a month ago I was presenting how to create plots from a PKTK analysis, and those plots were created with Phoenix, but also plots created with software R. In our second session on this example, I want to make you aware of the benefits of preclinical sparse NCA analysis and population modeling. And here the focus will be on population modeling. Since this is an express webinar, so a short webinar, we will not be able to cover any statistical background of population modeling. Rather, we want to provide a hands-on training and show you how you can build and validate your model using the software. If you're interested in gaining a theoretical background, please visit our Certara University page for a range of on-demand courses that we offer in this area. And in general, if you have questions or comments, please use the Q&A panel at the right-hand side of the WebEx console. And for the most frequent asked question, please note that we will share the slide deck, the Phoenix project file, and the recording after the event on our Certara University page. Let's switch on. So the goal of this webinar is to build a bridge from our well-known NCA analysis to the perhaps not so well-known Phoenix model. And that allows you to run population analysis. As some of you may know, you would need an additional license to get access to the population mode in the Phoenix model. This is called an NLME license. For academic users, this is already included in the license bundle, so you might have this functionality already available. For commercial users, you may need to check. If after this webinar you conclude this is a useful addition to your workflows, you might want to try it out. So back to our example from last session. As we have seen, we have analyzed a 28-day tox study in rats. Where we had 4 treatment groups: vehicle, 3, 6, and 9 mg per kg. PK samples were collected in satellite groups on day 1 and day 29. We had 3 animals per group, and we had female as well as male groups in our study. Samples were collected at dose time, 15 minutes, 1, 3, 6, 12, and 24 hours after dose. On the right-hand side, just to refresh our minds of what kind of data we are looking at, we can see a few plots that we created during last session. On top is just an individual plot, in the middle a summary plot, and at the bottom a PK parameter plot showing how the AUC relates to the different treatment groups.
Hi, Bernd. The slides are not advancing. Your slides are not advancing.
Oh, then I don't have control over the slides from here. For me, the slides are advancing.
I will be glad to help you.
I'm advancing them for you. Yep. Let us know what slide you want to be on.
Sure. Can you go to the next slide, please? All right. So yeah, just as a reminder of the example from last session, here are the details of the experimental design for an 28-day study in rats with 4 treatment groups and satellite groups for PK. On the right-hand side, just to illustrate some of our plots that we created during last session, an individual plot on top, summary plot in the middle, and on the bottom, how the AUC relates to the different treatment options. Can you go to the next slide, please? Anna? Oh, yeah. Okay. Now, coming to the benefits of preclinical sparse NCA. As this is shown here, in small animals, you cannot take enough blood sample to cover a full profile. Full PK profile, so you have to split it up into groups covering certain sample points, and that is illustrated in this picture. The color of the data points are grouped by the individual animals. So you can see that most of them are contributing just 2 sample points. There's one group of animals that is contributing just a single sample point around Tmax. And what sparse NCA is doing is it is summarizing all the data, generating mean profiles, and doing the NCA on these mean profiles. Can you advance the slide, please? So here's a result of a preclinical sparse NCA. You get a table of final parameters, like is what's shown here. But and here you get all the range of typical PK parameters like lambda z and Cmax AUC. But in addition, you have 2 columns calculated with standard errors for Cmax and AUC, and this comes out of the sparse NCA option. What I've shown in the last session is how to calculate some plots and PK parameter ratios from this analysis, from these plots, so we'll skip that here. Also, what you would need to do is you would need to create a number of tables for the report. And this we will cover in another webinar of the series, how to create tables from NCA final parameters. But that is actually all for today on preclinical sparse NCA. Can you advance the slide? If you want to get more out of this study, you would need to apply alternative methods. And here's where population modeling comes into play. There are a couple of things you cannot get from sparse NCA, and that is, first of all, information about variability, because NCA is only working on mean profiles. And population modeling is able to look at the whole population of animals as shown in this plot. And it allows you to split up the random components into inter-subject variability and intra-subject variability, or better, residual error. And it is this inter-subject variability, also called between-subject variability, that allows us to estimate covariate effects. And covariate effects enable us to explain some of the variability. So we have a means to quantify contributions from gender, from day, or from treatment. And this has a nice side effect, since the residual error is shrinking. When you are accounting for covariate effects, our parameter estimates are getting better. So you will end up with more accurate numbers. Last but not least, since at the end you have a model, you can also do simulations beyond the study data. So you can ask what-if questions. For example, what is the exposure after 6 months of dosing? Or you can use the model to scale up to human, do some allometric scaling. These simulation questions cannot be covered in today's session, so we have another Express webinar especially on simulations, where we will show you how to run those. Can you advance the slide, please? Now, when we do population modeling, we always follow the same procedure. And for our Express webinar, we want to keep it brief and simple to make best use of the time. So we can divide this into 3 principal steps: constructing a base model, extending this to a covariate model, and finally do the model validation. And also for the individual steps, principal steps, we can keep it rather simple for PKTK analysis. In step 1, we have to pick a structural model or compartmental model. And with sparse data, there's really not much of a choice. Given the few sampling points, we will always end up with a one compartmental model, since we might not have enough data points to justify a second compartment. Absorption is not much of an issue. In general, we just stick to first order absorption. Similarly, the residual error model, in most cases, the dynamic range stays within 3 log units, and that might favor the additive model. But as an alternative that you can always try out, there would be the multiplicative residual error model. And once you have achieved a reasonable fit with the structural model, you can explore some covariate effects. First, we examine this on a graphical level, but next, we simply run a stepwise covariate search to determine which of the covariate effects shows significance. Once that is done, we have our final model, which we then validate using bootstrapping and visual predictive check. Okay, can you advance the slide, please? So now let's look at the graphical user interface in Phoenix. It looks a little bit busy, but really there's not much we need to choose from. So for the selection of our structure model, all these options that you see here in this panel are all we need. We don't need to extend that. So in first, you see the population checkbox. We stick with population mode. Below that, the type of model will always be PK. And in the three tabs followed below that, we stick with the clearance parametration and extravascular absorption. And also for the start, we will just stick with the number of compartments equal to 1. You can see some other options and where you can simply change the number of compartments, or you can activate a saturated elimination, or include a time lag if necessary. But this covers most of the scenarios that are typical of PKTK studies. At the bottom, you see the options for the residual error model. Here, you can easily switch from additive to multiplicative and back. And while you're doing that, you can see the corresponding model code on the right-hand side, the statements. If you're interested to learn the code, just switch those options and see how the code changes. Next slide, please. Before fitting the model to the data, the program requires some initial estimates for the structural parameters. And here's the interface to the initial estimates tab, where you can see a preview of your model fit. And this is the first check whether you have chosen the right structural model. And for initial values here, what you need to add is Ka, which is typically 1, and volume and clearance. We typically go back to the NCA results, where these parameters have been estimated already. And you just take those NCA-derived values and enter them here. In most cases, like in this one, you can see that it already creates a nice fit of the curves. These are the predicted curves for these parameter settings to the observed ones, which you see as a data points in this panel. Before you hit run, you just need to check the run options. This is a separate tab in the bottom part of the slide. Most of these are just kept at the default. These are just very good starting values. And the run mode needs to be simple, which means we only want to fit the model to the data. Next slide, please. Once you have achieved a reasonable fit with your structural model, you can start exploring your data for covariate effects. The covariates can be simply added through the graphical user interface, as you see here. And then you can choose on which structural parameter you want to apply them. What is helpful is a graphical analysis from a simple fit of the model. For categorical covariates such as day and gender, you will get those box plots in the top part of the slide, where the plot shows the distribution of the eta values, or the correction, the subject between subject variabilities with respect to the covariate. And these are just correction factors or fudge factors of the population value of a structural parameter. In the first box plot on the left, it shows the subject-specific correction to the clearance parameter. Here, the median and mean values are higher for the day 29 compared to day 1. So this might be an effect that we want to check with our model. In the middle, this box plot shows the individual correction to clearance with respect to gender. That's a typical gender effect, and these are very common in red studies, so there's no surprise here. On the right-hand side, the plot, there's an XY plot of correction factors with respect to the treatment. And here we take treatment as a continuous covariate with increasing values from 3, 6, and 9 mg per kg. And you can see an increase of clearance with increasing dose levels, which may indicate some autoinduction process. Now that we have seen which covariate effects to apply to which structural parameter, we now need to click on those options in the panel below. There's just a yes or no that you need to select for the individual combination of covariate and structural parameter. And the next step, once you have set all these, you can run a covariate search stepwise. This you can select under the run options, and where these covariate effects will be checked individually in a stepwise fashion to add to the model, and they will be accepted if the significance is high enough. Next slide, please. And the resulting model that comes out of the covariate search is also called the covariate model. And for our Express webinar, this is already our final model, so we won't do any further modification of that. And with the final model, I can quickly go through some of the major diagnostics that you should look at. The first table is the overall table. It gives just the scenario name and a return code. 1 in this case, and that means that convergence has been achieved, so all is good. The following numbers like log likelihood, -2LL, AIC, and BIC are just diagnostic values derived from the objective function value, which is -2LL. And these numbers only make sense when you compare two models, and the lower the value, the better the model. And the next table below the overall table is a theta table. These are so-called fixed effects and show the population values for clearance and volume, as well as for all the individual covariate effects like gender and volume and clearance. Then another table is omega. This table shows the intersubject variabilities on clearance and volume. And on the right-hand side, the first plot is called POP-DV IPRED versus IVA. This is nothing else than the observed and predicted concentration versus time. On the bottom row, another series of plots. The first one is the residuals versus the predicted concentration. This is called CWRES versus PRED. And in the middle, we have the quantile plots for the ETAs, the random effect showing a normal distribution of those values, and the same for the residual histogram on the right-hand side. This shows the conditional weighted residuals, the histogram, and all the diagnostics that shown here, the tables as well as the plots, show a reasonable fit, a reasonable outcome of our modeling exercise. Next slide, please. So diagnostic plot is one way to see whether the model is good, but there are also methods for model validation, and Bootstrap is one of them. In Bootstrap, we create a large number of new training sets from the original data and fit the model again. And this model, this method will test the robustness of the model. And if the model converges roughly to the same final estimates all or most of the time, you shall be good. And what the program does, from all those fits, the theta values are summarized in this boot theta table. You just need to make sure that your estimates from the final model fit within the confidential intervals of the responding values in this boot theta table. Next slide, please. Another validation method is predictive check, or in this particular case, a visual predictive check. And here you are creating a large number of subjects and predict their concentration. And then you just plot the observed concentration from your study data against the predicted concentrations and check for an overlap. But here you don't plot the individual predictions, you just plot the prediction intervals at levels of 5, 50, and 95%. And when you see that the shaded areas of the prediction intervals overlap well enough with the observed values, that's the blue dots, this confirms that you have an acceptable model. All right, that's all from the slide. Let me share my screen, and actually that's something I can't do right now. To go into the model stage, is there any reason why I can't share my screen? Ah, yeah. Okay, can you see this? Wait a second. Here's my model. All right, so here we are in Phoenix. So this is the project file, and as we've started with the last session, we had two data files, the dosing records and the samples from our PKTK study with all the information here, sampling IDs, subject groups, time, concentration, and treatment. And what you need to do in order to make this a standard workflow, you link your imported study data with some data links. And these data links just take care of that you have the right column information in your input data that you can use subsequently in the downstream objects of the workflows for samplers and dosing. And for the preparations, here are a little bit, the typical steps that we did last time as well. So to prepare the samples, we need to get rid of the control, the vehicles, and also the pre-dose records. And what we enter into this is also a continuous time. Since we have times from day 1 to day 29, you might want to model based on the continuous time scale. And also what we are going to introduce here is a dose group which gives integer values for the dose information, 3, 6, 9, and mg per kg. Then we prepare the dosing by animal, and here, same steps, we just filter out the controls, and we insert the time record of 0 for the first dose. And now you have to make up your choice. You can either model on a continuous time basis, where you have to specify how many doses you have on this. So for example, additional doses, the number of additional doses after the first one is 27, so you come up with 28 doses. Or you tell the program, at day 29, I'm already in a steady state, so I don't need to provide the individual dosing information. So in this case, you just set a value for 1 when you reach the steady state at day 29. And this is what we provided here in this scenario. Same with the dosing by group, which we would then need for the NCA. So here are the two plots that I showed in on the slide deck, the population plot, and also the sparse NCA plot with all the animals. For NCA, what we are doing here is really we have the samples as our main input, and we have the dosing records from our input, and then we just activate the sparse option, and this will give us then in the final parameters pivoted table these PK parameters with the inclusion of the standard errors calculated for Cmax and AUC. So this is NCA. You can summarize those values. I've just did it for the volume and clearance because this will become important later on. So these are just mean values from this analysis. But then when we want to start with population modeling, we just take our samples, the results, and we link this to a Phoenix model input. Just put it on the bottom here. And here you see, before mapping anything, we just make sure we'll get all the options set here in this box in the bottom panel. So population stays on with population. The type of model is a PK model. We'll stick with clearance parameterization, switch to extravascular. And here we just stick with the one compartment, number of compartments. And also with the additive residual error model, you can simply switch to multiplicative if you want, but to keep it simple, we just stay here. And then we just go to the main mapping and show, okay, what do we have here? We have as ID, in this case, the animal ID. Time is time, and concentration is here called COPS, concentration observed. So we stick to this. Now the next step is the dosing, right? We need to do the dosing records. So we take these from prepared dosing by animal, right? Take it here and take animal on ID. Dose is called AA, amount absorbed, and time is time. An additional input, as I showed, was the steady state. So you need to switch to the input options tab and just click on steady state. And here you just enter a little bit of data. The dose point here is this value, AA. And the amount is actually a column, in this case dose. And the delta times the dosing interval is 24. But what it requires is the integer, you know, that when is the dose at steady state, and that is exactly here at SS. So you map this, and then you have the mappings done. The structural model is done, the residual error model, the input options. Now we go to initial estimates, and here you need to enter some of the values. So you see here already a predicted curve for those parameters, which are the default ones. We just stick to maybe 24, and typical value of Ka is okay. Volume and clearance we just take from here. So we go to the bottom. Volume is around 12,000. And clearance around 2,000, so that's what we can take. And just enter here again. So we put this one here, 1,000 and 2,000. Okay, this is just a single animal with 2 data points. It's better to look at all, so we take the overlay, and here you see already that it tries to fit the curvature of the data points, and also we can look at it on a semi-log scale. So you can see these values are already a nice fit, so we just accept them and would run the model. So this is what I did already here. This is the animal model, and this is the outcome. So you get here the theta values and also the fits. Is it? Yeah, the fits to the model, right? Okay, it's a little bit difficult to see, but the next step in running through this interface is we have a reasonable fit, but the next thing is we want to look at covariates. And we can pick those from the parameters tab under the structural. You can add from unused, and here you see already there are some like sex or day and the dose group that we can simply add, and then you have them presented here, and you can simply add those to the model by switching these on or off. So sex and day is categorical, but dose group we can center at a value of 3 because 3, 6, 9, we can center at 3. This is our first dose. And we can set some of the covariate, a categorical covariate, like day is a categorical covariate. Here we just switch it here to day 1 and day 29. And also sex is a categorical covariate, but here we allow for maybe individual category names like 0 and 1. And take it from there. And then the next step is you need to check which options here make sense. And for this, you run a simple fit using no assignment of covariates, right? And then you get those plots here in these covariate plots, pop covariate box plots, where you see there are some on clearance. There's a covariate effect of day on from the difference between day 1 and day 29. Same for the sex, for gender 0 and 1. And also on volume you have kind of a covariate effect shown in these plots. For the continuous covariates, you see also a slight increase of the dose group, the different treatments on the clearance and also on the volume. So in order to check which are really significant, you need to check those boxes on. And you see it just adds the code to these values. And by doing this, you can simply see, how you can enter those maybe on your own. Next step is actually we don't need random effects on Ka, so we just stick with that. Okay, with that, we can run now a covariate search stepwise that will check each contribution individual and add up using those criterions for adding and removing those, using those p-values to show whether they are significant or not to add. And once you are done with it, you end up with a final model, which is this. This is your final model, and you saw the diagnostics already, on our slides with overall and omega tables, as well as with our histograms that we've seen, right? And okay, as a residual histogram. Once that is finished, you can then go to the bootstrap. This is just under run options. You choose bootstrap for the validation of your model. You select a large number like 1,000. You could stratify by a categorical covariate like day or gender, but we just stick with those, and it tries to fit 2 times. And this is very time-consuming, so I've executed on an external grid so that you get the results very quickly. And here's the outcome. It's a boot theta table where you see, all the summarized values from those 1,000 fits. Next thing is VPC. The visual predictive check is also just an option here under run options mode, and here you just pick a number of, again, maybe 1,000 replicates, so 1,000 subjects to be created, and you put it on the x-axis as time. In this case, you would use explicit boundaries, but you can also use a k-means or explicit center, but in this case, where we don't have very many sampling points, it makes sense to give it some manual boundaries. And also what you're looking for is some quantiles at like 5, 50, 95 in order to get those shaded plots, which show you, a reasonable fit of the predicted percentiles and prediction percentiles and the observed percentiles. We said, I guess we are roughly at the end. Maybe just the final thing. Typically, what you want to do is in PKTK studies is you want to get an estimate of AUC and Cmax, and then it's actually simply put into a textual mode. You just need to switch here to the textual mode and then enter these 2 lines of code in order to get the AUC automatically calculated Tmax and Cmax as well. These are the 2 lines you just need to add. You just switch to textual mode and add those 2 lines. And then under run options, you can ask for them to just add in another simulation table where you enter maybe the time, the end time, 24 hours, and put in Cmax, AUC, whatever parameters you want to get. And these are then showing up in one of those simulation tables, like here. You see you've got for each animal your calculated Cmax, Tmax, Cmax, and AUC. I guess with that, I'm at the end. I guess we'll get to the Q&A if there's time for that still.
There's probably no time for Q&A today, but there's a couple of questions that we will address when we send the link to this recording.
All right. Yeah, can you advance the slide, Anna, then? Just maybe one. The next one. Yeah, there's a next session on in this Express webinar series with quick and easy customized tables. This is what I already mentioned during this session. In 4 weeks' time, on April 16th, we are presenting how to create these tables. So if you're interested, please join, and we're happy to see you there. With that, I guess we are at the end, and thank you all for your attention, and talk to you next time.
Thank you, Bernd.